Okay, let's make a start. So, for today's class, we're going to have a look at how to handle the application style questions, specifically around circular functions. So, up until now, we've done pretty much all the theory on how we do circular function stuff. We're now looking at how we can apply that to the extended response style questions. So, for the first part, we'll be working out of the screen share, and we'll take it from there. So, applications of circular functions. Basically put, you'll be given some sort of scenario, if you see in the example below, and most of the time the goal will be to create a function out of that scenario. You can see in the example we have a fully generic circular function, and the goal is basically to fill in all of the unknowns in that circular function. That's one of the most common things that come up. The other most common thing that comes up is after you've created that circular function, now we need to interpret what's going on. In the context of this one here, we have some sort of tidal wave situation going on. You might be asked to figure out how long will there be a high tide for? How long will there be a low tide for? What will be a high tide as far as like how tall it is? These sorts of questions are how we essentially break down and try to analyze the function that we're left with. So, broadly speaking, there's no real step-by-step stuff you can do for this because every question is going to be slightly different, but there are commonalities that are across a lot of the application style questions. And so this is less of a step-by-step guide and more of just some guidelines on what is typically easiest to do when it comes to solving these circular functions. Typically, it's easiest to find the period first, then vertical translation, amplitude, and then horizontal translation. But that's just a bunch of text. Let's see how that actually applies to one of the examples. This one I pulled from the Cambridge textbook. So, as I said, we have a tidal wave sort of situation going on. Time between high tides is 12 hours. Average depth of water, high tide. H of t is telling you the depth for any given value of time. So it says specifically, assume that the depth of water, h of t in meters, at this point is given by that equation. So if h is on the outside and t is in the brackets, that means that h is going on your y-axis and t is going on your x-axis. H is the height of the wave, or in this case it's written as depth, and t will always usually be, well, pretty much always is going to be some unit of time. Then after that, it'll tell you something about what t and what h are. In this case, it told us about h before. This time, it's talked about t afterwards, and it said that t is the number of hours after noon. So that gives you a bit of an idea. T is in hours, specifically hours after noon. So, first thing that's usually easiest to find is the period of the circular function, and that's going to help us get the n term for our circular function because any circular function can have its period be calculated by 2 pi divided by n. Well, I should say more specifically sine or cos. Tan, if you somehow get a tan one, will be pi over n instead. So, the period will always be the time in which it takes the scenario to repeat once. That's what this statement here is all about. The time between high tides is 12 hours. So going from high tide to low tide back to high tide is 12 hours. That means the period is 12 hours. So capital T period is going to be 12. Capital T period is also 2 pi divided by n. So 12 equals 2 pi divided by n. Rearrange for n, that's one letter down. Any questions so far? Easy. And if I go too fast, if you have any questions, feel free to leave them in the chat. No worries at all there. Happy to go back. Next easiest thing to do is typically to find the vertical translation. So where's the mid-level of our circular function? It really does help to think about things in terms of mid-level. The other key word that comes up a lot is average. Whenever you're talking about averages of circular functions, it's always the midline that goes through from peak to trough. So if I go to the handwritten section, just to do a quick demo of what that looks like, if your circular function looks like this, the midline there is both the vertical translation term and it's also the average of the circular function. It's the middle that goes through it. So if we're told the average depth of water is 5, that means our vertical translation is 5. In this case, they've used the letter B to determine that. There won't necessarily always be a way where you'll be given it immediately. You might have to calculate it. If you know the peak and trough, for instance, you can always find the middle by just doing the midpoint of that. Peak plus trough divided by 2. So if I know my peak and my trough, I can always calculate midpoint as well, based on that. Next easiest thing is to probably do the amplitude. So specifically the amplitude is the distance between the mid-level and the peak. So you either know what your peak is, or you have to calculate it. You either know your peak and middle, or you have to calculate one of the missing things. In this case, I believe we have both. Let me just double check. We have the middle, that was the average of 5, and at high tide, we have a depth of 8. So high tide is going to be the highest h value, highest y on the y-axis. And so that's going to be your peak, 8 meters. So the amplitude is going to be the difference between those. 8 minus 5. So we have an amplitude of 3. Worth pointing out, technically speaking, your capital A, the A value at the front, could be both positive or negative, completely dependent on what your horizontal translation is. So even if you do pick a negative number for whatever reason, you'll still be fine, because as long as you have a horizontal translation term to work with, whatever you choose your horizontal translation to be will fix whatever your choice is. So basically, don't have to worry about whether A is positive or negative, just stick to 1 and you'll be able to figure out you'll be able to solve the question regardless. Alright, so let's recap. We've got our N value, we've got our B value, we've got our A value, and so if we look at this function, we've only got a few more unknowns left. We don't usually consider h of t and t to be their own unknowns to solve anyway, but they're technically unknowns. And the other one is the horizontal translation. That's the only one that's left to actually solve for to get the equation that we want to have. So if I want epsilon, that horizontal translation, I need to fill in my t and my h of t. That way there'll only be one unknown, and I can solve for that relatively easily. There's going to be some piece of information in the question which will help you do that. That's what this one here is. At noon, there is a high tide. So noon is a time value, high tide is a height value, or depth in this case. Noon is t equals 0. And the reason why is because t is the number of hours after noon. So specifically at noon is no hours after noon, so t equals 0. High tide is going to be 8, because we're specifically told the depth at a high tide is 8. So we have t equals 0, h equals 8. We plug those into our equation. So there's our h equals 8, our t equals 0. And that is just a circular function that we can solve using the methods we're already familiar with. So we rearrange, subtract 5 from both sides, divide by 3. That gives you 1 equals sine of epsilon. And then using the unit circle, we can find a pretty easy solution to that, pi over 2. So if you're not already familiar with the unit circle, well, you should be. You'll need it for pretty much everything you do in circular functions, assuming you're doing circular functions at your current stage. That's pretty much it. You now have your epsilon value. Technically, you can pick any valid solution. Like you could go all the way around to 5 pi over 2, or you could even go negatives if you wanted to. They all work, but don't make things harder than they should be. Just stick to the easiest one that you can find immediately. One thing that definitely is worth talking about is how you can change things if you need to. So in this case, we're happy because we were told to fill out a sine equation, like this one here. We were told to just fill this out. If we were just sort of given free reign to do whatever we wanted, or we had to transform that in a certain way, make it a cosine, for instance, that's where using our trig identities can be kind of helpful, right? The main one that comes across when converting between sine and cos is going to be your plus or minus pi over 2 type equations, because those will always convert you between sine and cos. The way this one works is simply we have something plus pi over 2, and it's sine of something plus pi over 2, which means we can basically just knock off the plus pi over 2 and replace sine with cos. That's all this one says. So we go from here to here. There's no pi over 2 to be seen, and sine has become cos. That's a neat little transformation to keep in mind in case you do have to, for whatever reason, convert between sine and cos. But for most circumstances, just leaving your answer here should be fine. In fact, your CAS might literally just do this for you. If you plug this in, it might just give you this. But okay, those are the fundamentals there. Is there anything I need to clarify further on that? I've really only gone through one example. I think one thing that might be helpful here is to go through another one live, and then what I can do is I can pop up the breakout rooms and we can go from there. So let's see. We have a look at question 1 here. What we have is an actually solved circular function, so that's nice and easy for us. What I'll do, just to save a bit of time on this one, is do a bit of CAS work on it. That way we can, well, yeah, save a bit of time. So first things first is draw the graph. We're not really focused on our sketching here. We're also focused on the applications. So sketching the graph, if you need to revise that, there's resources or past recordings if you want to have a look and revise how to do that. So what I'll do instead is just sort of CAS that one out real quick. So let's define our function. I typically call things h of x as I know where that is on the CAS, because the CAS decides to do an alphanumeric keyboard as opposed to a QWERTY keyboard. 5 sine of pi over 6x. So don't forget to specifically use x in these cases, because if you don't, the graphing tool won't really know what you're talking about. So you do have to be aware of the fact that you have to sort of rewrite things a little bit. But okay, that's our graph. I can even change the window settings a little bit to make more sense. It does say sketch from 0 to 24, so we're going to sketch from 0 to 24. And that gives us our graph. As far as copying that down, I mean, you've got your analyze graph tools. So in 6, you would grab your min and max. You can grab those and copy those down onto paper should you wish to copy that down. Okay. So part B, when was a high tide? First thing you want to think of is, what is this function even about? It's h of t. So what's going on the y-axis and what's going on the x-axis? Anyone want to take a swing?
Chris, since the amplitude is 5, does that mean like the y-axis needs to be at 5?
Repeat that one, sorry?
Since like at a high tide, right?
Yep.
Because the graph has an amplitude of 5, that means the y coordinate would be 5. So
Mm-hmm.
can't we just solve for where the y coordinate is 5? H of t is equal to 5.
Yeah, absolutely. Yeah. So basically the underlying idea there was that this is h of t, so height is on the y-axis. And so you've been able to identify that, yes, if we're looking at amplitude 5, that means all of these peaks are going to be y equals 5s. And so yeah, fundamentally all we're going to do is solve for where height is 5. 5 is equal to function, comma, x. Obviously, if you're doing tech-free, you would have to use your other methods. We're not so much focused on that in this one. 0 less than equal to x less than equal to 24. Don't forget to put a domain on this, otherwise you will get a whole bunch of different solutions. For instance, if I cut this one off here, you will get an n term in there. That's because circular functions repeat forever. But okay, that's going to give us our two t values. T equals 3, t equals 15. The only thing you have to consider in an application style question is that t equals 3 and t equals 15 isn't a great answer. You've got to write it purely in terms of the terms they're using in the question. So how do we convert t values into something that's more meaningful in terms of like a when? Like if someone on the street asks you when was a high tide, what could you potentially say?
Could you say, hold on. let me just read the question real quick.
Yep.
Would you say 3 a.m. and 3 p.m.?
3 a.m. and 3 p.m. Correct. Yeah, you take it in terms of hours and you break it down into the actual time. It says when was a high tide. It doesn't say solve h of t for 5. It doesn't actually say that. It says when. So you have to give a time. And you can even use the context clues of the next few questions to help you with that. You know, it gives you time values in clock times, and so that's the context under which you would give an answer. That's pretty much it, really. So what was the height of the high tide? We already said that one. That's going to be 5. We saw that already. What was the height at a specific time? Well, if you know the time value, how might you get the height out of that? Kind of like the reverse of what we did.
Plug it in
Yeah.
the T, solve for.
Yeah, you plug it in as a t value, absolutely. So 2 a.m., 2 p.m., we have the opposite issue. Now we've got to convert 2 a.m. and 2 p.m. into a t value. So if t is number of hours after midnight, 2 a.m. will stay as 2, but 2 p.m. is actually 14 hours after midnight. So you'd plug in t equals 14 for that. But otherwise, yeah. And then lastly, a boat can only cross the harbour when the tide is at least 2.5 metres above mean sea level. When could the boat cross the harbour on this day? This one's probably the hardest question in in question 1. I'll let you guys have a little think about that. In fact, I can even show the graph as well if you want to make reference to that. Only cross when the tide is at least 2.5 metres above mean sea level. Yeah, any thoughts?
Do we just solve for when the graph is above 2.5?
Yeah, exactly right. So to put a visual on that, if we have a look at the handwritten notes, or the CAS rather, if I put in y equals 2.5 in there, you basically want to be above that line. So we're talking mean sea level, 2.5 meters above mean sea level. The thing you need to identify there is mean sea level is just the average, or the middle line. So 2.5 meters above just means 2.5 above 0, which is why we're doing this line here. Then from there, because we want to be above that, we want to figure out the intersection points at all these stages, and then be above. This is where having a graph can be nice. Otherwise, if you're doing it tech active, it's pretty chill, because once again, it's going to be a CAS solve. Function is greater than 5. Oh, sorry, not 5, 2.5, my bad. This probably isn't an exact value, so I'm assuming we're going to get some interesting decimals. 0 less than equal to x less than equal to 24. Yeah, okay. That's a bit odd. We're still getting n values. Greater than 2.5. Yeah, maybe it doesn't play particularly nicely with the greater than sign. That's still fine. If we just make use of that, we'll get all of our breakpoints. X equals 1, 5, 13, 17. And then we can just use logic and say, well, that's 1 and 5, and so between 1 and 5 is good. That's going to be 13, 17, if I remember the numbers correctly. And so above or between 13, 17 will also be good. Everything else will be invalid. That's the skill, really. So all these individual things you know how to do. You know how to CAS solve for things. You know how to, you know how to CAS solve for things. And so really it's just a matter of breaking down the question into the key bits of information that are in there. Cool. All right. Is there anything left to clarify on that question? Because if not, I will set up some breakout rooms and we can do some you can do some private study, either doing this thing if that's where you're at, or if you're doing anything else in your particular schooling, I'm happy to have a look at that as well. Okay, I think I got that one right. Awesome. So in the chat, you'll see a Word doc that has the prescribed questions for this particular class. It's the Chapter 14N and Chapter 14 review for the Cambridge book. In the Word doc is a link to the Cambridge book, so if you don't have it, you can download it from there. Specifically the Unit 1 and 2 book. Don't get the Unit 3 4. You can, but the questions won't line up. Unit 1 and 2 Cambridge. It says it in there as well. So I'm pretty sure the chat does persist through the breakout rooms, so still grab a copy of it, but even if you don't before you jump into the room, that should be fine. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Oh, full house here, my god. Can I even make enough? This will be funny if I can't. Oh, I can make plenty of them. We're good. Alright. Soon enough you will see the breakout room. And then we'll go from there. Right. I think I got everyone. Let's see how we go. If not, I've got rooms to spare. Oh, made it back here. Did the link break on you a bit?
No, it worked, and I just think I clicked back.
Oh, sure. Okay. I mean, I guess it's
Yeah.
fine if you stick around here. I'll still just be making my way around the rooms.
Oh, okay.
I'll give you another request just in case. Oh, no, you should still be able to. If you look at the bottom, you should see like a breakout rooms tab to be able to jump back in, I believe. But if not, that's fine. So whereabouts you at in your studies?
We're currently doing chapter 18 at school.
Chapter 18 on the Cambridge?
Yeah.
Yeah, okay. What's that? Let's have a look. And how are you going with that? Is there anything in there you wanted me to have a brief look at?
Currently, after school holidays, I was a bit busy. So I was basically finishing off my chapter 17.
Yep.
Like the limits and anti-differentiation.
Mhm.
So currently, I'm kind of just starting 18, to be honest.
Sure, okay. So if you're just
Yeah.
starting, I guess, yeah, probably better off you see what you can do, right? Do as many questions as
Yeah.
you can there. And if you're having any actual troubles with it, I'll be there to sort out any particular issues.
Yeah.
All right, cool. I'll leave you to it.
Yeah. Thank you. Also,
yeah.
can I just ask, what resources in the school thing can we use to help with this chapter?
With 18 or with what
Yeah,
we're just
with
for 18 that's going to be the calculus in diff. So you're looking at applications I think the chapters are literally called applications of diff in the school.
Okay.
It'll be under calculus.
Yeah.
If you're still unsure, just text my school chat, text my school account, and I'll show you exactly where it is.
Okay.
Easy. All right.
Cool. Thank
Hello, hello. How you been going? You're currently muted, by the way.
Yeah, it's just funny. I found, not bad. I mean, because I think we might do it a bit different. I'm wondering if that's what topic everyone else is on at the moment.
Oh, everyone's going to be doing different things if they're
Different
unit
things,
1 and
yeah,
2,
okay.
which is why in the breakout room I'm like, okay, you might not be doing this, but at least here we can spend 5 or 10 minutes where you're at.
Yeah, because it's definitely because I'm assuming you use this mostly next year.
Next year. I mean, this is a Unit 1 and 2 thing
Oh,
specifically,
but
but it's circular functions.
yeah.
You'll do it at some
Um,
point.
yeah, because we did this in Unit 1. I think it was the last topic we did.
Yeah, okay. I mean,
Okay.
I guess what I'll ask is there anything in particular you'd like me to do a quick, like, 5-10 minute thing on?
Um, if I can, or I might get you to come back. That's all right.
Yeah, okay.
And
I mean, I'll do the
yeah,
rounds.
yeah,
Maybe even for next lesson, right? If you're able to attend that or the one afterwards. There's a place where you can actually drop off your questions ahead of time, so that way I can even have a look
yeah,
at it and be prepared with the thing.
yeah,
And that gives you time to prepare, of course, for the class.
yeah.
So
Okay,
I'll
cool.
keep doing the rounds a bit, and yeah,
Yeah,
till then,
cool. Thank you.
no worries. Hello, how's it going, Steph?
I'm good.
Having fun?
Yes.
Cool. So, are you working on any of this stuff, or do you want me to have a look at anything else in particular?
I was gonna ask about the thing you said about converting sine to cos.
About converting sine to cos?
Yeah, because I've never really heard about that.
Oh, sure. Yeah, okay.
Or,
Yeah, no, understood. It's not usually framed as converting sine to cos. So what I'll show you is where that actually came from. You'd probably know it under symmetries of the unit circle. That's where you might have seen it for the first time.
Mhm.
So what I'll do is I'll pull up the notes on that one there, which, yep, screen share is looking at. Good, I can do tech. So have you seen anything like this before?
I don't think so.
I don't think so. Okay. Let's see, where is it on the chapter? It's going to be under either 14J or 14D. Have you done any of those chapters?
Probably have
Probably have. Okay, I'll scroll over to
a term or two to go. I don't know.
yeah, at some point in some distant past memory. Yeah, so you might recognize anything like this. This
Oh
might-
yeah.
Yeah, okay. So you'll notice here that there's sine equals cos, there's cos equals sine. You know, there's ways to
Yeah.
convert between them. It's not usually framed as converting, but it is more so framed in the sense of symmetry stuff. So where that comes from is the so-called quarter period formulas, which are all of these, which looks like a massive mess of nonsense there. But where I find is a bit easier to try and digest is when you do these so-called reference angle formulas. So I think the fundamental here is to look at the base angle that you have. So I'll go to an actual question. In this case, we're told a piece of information that is cos is equal to 0.72. So what you do, it doesn't matter what any of this says afterwards, you start by drawing the unit circle thing, and you draw this red reference angle here. You're going to label it with an x and a y component. Only one of them, usually, is going to be knowable. Right? So if we have cos is equal to 0.72, then the x is 0.72.
Mhm.
If we had sine, we would do the y value. Now, when it comes to pi over 2 plus or minus theta, what's going on is whenever you have just like a fixed angle there, in this case pi over 2, that tells you your new starting point on the unit circle. So instead of starting at 0 and then going in an anti-clockwise direction, you start at pi over 2 and then go in, depending on what this is, will tell you what direction you go in. Cool so far?
So it's just an inverse.
An inverse.
Like-
I mean, technically, very technically speaking, yeah, that is an inverse because you're swapping x and y.
Okay.
Yeah, no, that's one way of thinking about it. Yeah, it's an inverse. More so, you can think of this one as an inverse. The problem with that is that there's others, right? Like there's negatives, which will do this. There's pi plus theta, which will do stuff like this. It's a bit less helpful to think about it in terms of an inverse. Rather, probably think about it in terms of this tells you the starting point. So this one
Mhm.
here, for instance, pi plus theta, this pi tells you start at pi, and then plus your theta.
Yeah.
So in the case of the converting between sine and cos, the reason why there's a conversion at all is because when you do pi over 2 plus or minus theta, what happens is you do that inverse, you do that swap, like you mentioned. And because you swap, if x is cos and sine is y, then, well, you just swap from sine to cos, because now you're swapping the location. So that's where that comes from. Is that clear enough?
So from going to like sine and cos, you're switching the y into x value.
Yeah. Now, more specifically, it basically means whenever you have pi over 2 minus theta in sine, it becomes cos. And the reason why is because if you start, it's easier to think about the original one. So if you start at cos, pi over 2 minus theta means take this thing, start at pi over 2, and go backwards. And because you're going backwards in the same quadrant, that pi over 2 one, you flip them. And so when you read this thing specifically, this is the same as this. This is sine of pi over 2 minus theta. This is cos of theta.
Okay.
Because they're the same number, we can say they are the same thing. So that's a bit about where it comes from. So what I'll do for you is I'll do a copy of the summary of all of these. It'll look like a bunch of text, of course, but having a look at these actual resources and seeing where they will come from can give you a bit of a deeper understanding as to where that came from.
Okay.
So, okay, I'll pop that one in there. Direct to you. Awesome. Okay. This one will be under circular functions. I think it's like one of the last bits in the chapter, in the school thing rather, which is I think I called it symmetries of circular functions. If you can't find it, let me know on the either via text or via school, and I'll help you out with that.
Okay.
But otherwise, yeah, that's all we're using. We're using those conversion formulas. You don't really have to know where it came from, as long as you can see, oh yeah, this equals that. Cool, got it.
Now, what situation do I use it? Does the question like tell me if they'd want me to do it in a cos?
Yes, yeah, they'll tell you it's like, hey, here's this nonsense thing. What does it also equal? And then you have to think about all these ways in which you can rearrange things. Like even as simple as like, it's pretty helpful when it comes to multis, because what they'll do is in multis they know you use cas, and so to stop you from just casing it out and solving it immediately, they'll give you circular functions in the multis, but they won't look like what the cas will do, and so they'll force you to have to think about, oh wait, okay, so I have negative sine theta, but that is the same thing as sine pi plus theta, which is what is on the multi. So they'll have to make you do another half step on that.
Yeah.
That's where I've seen it come up most.
Okay.
Cool with that?
Yeah.
Awesome. All right. I'll leave you to it for a bit.
Okay, thanks.
No worries at all. Where to go next? There we go. Hello. What's on the agenda for today?
Hey, I had a few questions from a practice sack.
Okay. This will be okay. Have you got them ready to shoot?
Yeah, but can I like send them to you?
Yeah. Okay. Cool. Let's try send it to me. Are you going to do it text or school or where are we going?
I put on chat.
Oh, awesome. All right. Cool. That is quite a few questions. I don't know if I'm able to do all of them. I do still have to talk to a few other people. Is there any one of them in particular you want to start with?
Could we start with the first one?
First one? Sure. Okay. And a good idea probably would be to send these. You know, there's a link in each of the calendar tabs that you can send questions to. Granted, I didn't actually look at it this time because no one uses them. But if you're looking to do multiple things, maybe send it ahead of time so I can do a written thing and get through more of them in a shorter time.
Okay.
But okay, cool. Without calculation, explain why the average value is 0. I can't actually hear the question on.
Wait, not for that one.
Oh, yeah.
The question 3 seesaw.
3. Oh, okay. That's a completely different one then. Where is it? 3 seesaw. Let's find that. That might have came out of order a bit.
Yeah.
Question 4. Question 3 seesaw. I mean, there's no actual question attached there. It's just the. Well, maybe
Yeah,
there's.
and then it's
Oh,
you find
yes.
the coordinate
Yes.
of A dash.
Okay, E. Yes, cool. All right, we got some big polynomial. Find coordinate A dash, which is a tangent off of that. Find coordinate A dash perpendicular to L1. Cool. All right, so while I have a think about what's going on here, I'm going to grab my camera in here and hope that it doesn't crash, because I still haven't figured out why it's crashing. I guess it's just an old phone. Okay, we're in room 4. Let's pull that in. Okay. So polynomial is g of x. That's going to be the whole thing there. Perpendicular to L1, so I need to know. I mean, one of the first things I'm looking at there is that it's perpendicular. And so that usually means you want to, instead of finding the gradient of the A dash line, you start by finding the gradient of the L1 line. Have you given that a shot?
No.
Not particularly. Like, how much of this have you done? Have you just seen it for the first time, or
No, I've had this a while.
had it so well? Okay. So was this just one where you had no idea where to start?
Yeah.
Okay. Let's make a start then. Cool. So perpendicular to me immediately means there's a relationship between L1 and L2, and that is that 1 is going to be the gradient negative reciprocal, -1 over m, of the other one. So m1, m2 are going to have that relationship. Remember that one?
Yeah.
Cool. So I've got no idea what L2 has got to do with anything other than the fact that it's perpendicular to L1. And so the next natural thing is what's got to do with L1? Well, I can see 2 points on L1. I can see A, which appears to be the x equals 1 of the polynomial, and I can see B, which is an x-intercept of the polynomial. So if I wanted to figure out gradient of L1, what would I do?
We want to get the coordinates of A and B.
Yeah, coordinates of A and B definitely helps for sure. How are we going to get the coordinate of A? A bit trickier to see. But yeah. Usually you're not supposed to be like eyeballing it, but in this one you can eyeball it.
Would it just be 1?
It'll be x equals 1, yeah. But we want the y value there as well.
Or would we
So,
just sub in the 1 into the original equation?
yes, correct. I'm going to sub in the 1 into the original equation, which I'm going to copy down. 7x power 4 plus 18x power 3 minus 21x squared minus 58x. Okay, that's going to give me h of 1, which is 3, which is a really nice number considering the size of that function. Okay, that gives us the a coordinate and then the b coordinate. What do you think we're going to do for that?
Would we make the equation equal 0?
Absolutely. Yeah, very good. h of x equals 0, comma x. We're going to get the second solution, which is going to be the x equals -2. You got to do a little bit of rationalization to figure out which of these is the b. Is it clear enough why that would be the x equals -2 one?
Yeah.
Awesome. h of -2 is 0. That's a rise of a run, so we got a coordinate 1, 3. We got a coordinate -2, 0. So our rise of a run for gradient is therefore going to be 3 over 3, because -2 to 1 is a distance of 3. Okay, so that gives us gradient of L1, which we can then find gradient of L2 by doing a perpendicular. So -1 over 1, we know the gradient of L2 is therefore -1. Following so far?
Yeah.
Cool. So now we need to take the tangent off of, we know the gradient of L2 is -1. We just need to figure out how that would work for the polynomial. How do we know where a gradient is a particular value on a polynomial? Or any function, I should say.
Is it the direction of where it's going?
Technically, yes. Yeah. What's the mathematical way we go about that? derivative. So if we know gradient's got to be -1, then we got to find where derivative is -1. Clear enough?
Yeah.
So we go about derivative. We put it in a cas solve. That equals -1, comma x. That'll only have one solution if we're lucky. If not, it's fine. We just take the furthest one because we can see it's clearly going to be the furthest spot. Which means the x-coordinate would be this. Do you have answers to look at?
Yeah.
Does this look like the x-coordinate?
Oh,
well, it's decimal places actually, my bad. So it would have to be 1.201-ish.
Yeah.
Okay,
That's
cool.
it.
So, in order, we knew the only thing about L2 was that it's perpendicular to L1. So we used that gradient relationship to find it. Then, because we know it's tangent, we also take the derivative and make it equal. Is that cool?
Yeah.
All right, cool. So that's one of those at least sorted. I'll do the rounds. I don't know if we'll be able to get through any more of them. Send them all through anyway, through like a text or whatever, and I'll write them up and give you a written solution to everything in my own time. How's that sound?
That'd be good. Thank you.
Happy to help. All right, to the next one. This makes a lot more work for me, I swear, but you know what? If it's better, it's better. Hey, how's it going, Shiloh? Having fun?
Oh, okay. Hello. You scared me. My room was pitch like quiet. Oh, I'm
Just a
doing
little.
good.
Yep.
I'm actually finishing up 14H. Oh my goodness, Chris, irrelevant, but like I have an essay exam in like 2 weeks. Oh no, not 2 weeks. It's next week now, actually. But yeah, I just had to be like to say that because goodness gracious, the workload is actually killing me. But I'm actually helpful that I have math. Like
Mhm.
if I didn't have tutoring, I wouldn't have been able to do my maths homework. Crazy.
Well, lucky you, hey?
Mm.
So I guess, is there anything in particular you'd like me to have a look at?
Not yet. I'm just working on the
Hmm.
questions that we worked on last time, and I'm trying to build on with 14I as well. I haven't finished yet, so if I need help, I'll just holler. But
Yeah,
right now,
sure.
I'm finishing up the previous work.
Easy. All right, no worries at all. And if you have any questions, of course, you can just text me afterwards or even say it for the next class. We can certainly go about that.
Oh, okay.
Easy. All right, till the next one.
Okay, bye-bye.
Hey, I made it.
Hey, how are you?
Yeah, doing good. This is probably one
Um,
of the biggest rooms, so it's taken a bit to go around.
no, that's all right.
How you going?
Not bad. Here we have question C. I want to go through, which I think I've
Question C.
figured out what I've done wrong.
Oh, yep. Okay. Solving for x in that circumstance. Sure. Okay. This is an example of using your log laws appropriately.
Yeah.
So, work me through a bit about what you're doing to solve that.
I was just x. I think it's you just do x plus 2 on 6. I think, right?
Yeah, it's exactly what you do because it's the subtraction law. You got the same
Yeah.
bases, and so when they're the same base and subtraction, you can do a division.
Yeah. Okay.
It's good.
And then I kind of forgot to do what to do from there because I haven't looked at math this week.
That's fine. So I'll start writing it out now on the second camera. So you've done the hardest part, which is good, because when you're at this stage, everything is the same from here. So
Yeah.
you're going to have log you're going to have log of something equals something.
Yeah.
And so under those circumstances, the only thing... sorry, did I do that right? Yeah, it's over 6. That's it. X plus 2 over 6 equals 1. Okay. So the good news is, once you're at this stage, it's the same every single time, which is what you want to do is go from log to exponential. That's at least the default way that works always. Technically speaking, there is one thing you can do that's even faster in this particular method, which is whenever you have a 0 in the bracket, you get 1.
Yeah, 1. Yeah.
So that's a that's a pretty easy way of going about it because you can just say x plus 2 over 6 equals 0. But to highlight why that is, converting to exponential. So here's your base, here's your power, and here's your, and here's your bracket. So that comes out the front, x plus 2 over 6, 4 to the, what am I saying? Yeah, 4 to the 1. 4 to the 1 is equal to that. I did just kind of misremember that actually. Putting a 0 in there isn't quite right. It's the other way around. When you have a 1 in here and this equals 0, that's what what it actually should have been.
Yeah.
So I've just kind of misremembered that.
It's all right.
So we'll forget about that one. Point being, easiest way to go about it is going to be convert to exponential. You can see already trying to do hacks, it's made even
Yeah.
a slip up. So I guess, is
Okay.
it clear how this has gone from point A to point B?
Yeah, I think so.
Yeah, so these two are a pair.
Yeah.
Base. So the way that I like to remember this always is, this is called the base of the logarithm. This is called
Yeah.
the base of the exponential. They actually have the
Yeah.
same name, and so you know they're going to
Yeah,
go in the
okay.
same place. Then from there, the way that I think about it is, the whole point of converting to exponential is to free all this x stuff. I can't do anything when
Yeah.
it's in the brackets, and so I would only bother converting if I wanted to free it out. So that helps
Yeah.
me figure out where that one goes.
Mhm.
And then lastly, there's only one place left to put this, so then I just know by default where to put it.
Yeah.
So that's how I think about it. And then from here, this is just linear, right? There's nothing crazy to talk about.
No, okay.
So we do our x plus 2, 24, x equals 22. So it's a
Okay.
nice and chill thing. So in order, first things first, you use subtraction law, super chill. The only
Yeah.
thing from there, once you've combined everything possible that you can down into one single logarithm, you flip that to exponential, and then you work from there.
Yeah. Okay.
I'll leave one more parting gift, which is, if you have logs on both sides, so log a, let's say x plus 2 equals log a x, you can leave these on the other side of each other,
Yeah.
and you can just make the brackets equal to each other.
Okay.
So as long as you have the same base logarithm on both sides and only one logarithm on each side, then you
Yeah.
can just go and say x plus 2 equals x, which obviously has no solution there, but this is just
Yeah.
hypothetical.
Yeah.
You don't have to bring this over, do a subtraction law, convert to exponential. If
Yeah,
there's
okay.
the option, then you can make use of this as well.
Yeah.
That's
Cool.
all fair enough?
Yeah.
All right, I'll leave you have fun with that for a bit.
That's fine.
Yeah, and yeah, one thing I will say, just as a bit of catch up for what's going on here, if you do want me to go through something specific, then the way we can do this a bit faster is if you submit questions ahead of time. I know there was a short turnaround for this, so it's hard for
Yeah.
you to do that.
Yeah.
But it saves me coming in here and having to come back and that sort of thing.
Yeah. Yeah.
So
Sweet.
that's
Thank
just
you.
a thing for next time. But yeah, all good. You're doing good. It's cool to
Good,
see that you're
thank
able
you.
to at least get most of the way for these questions. Only one little
Yeah.
thing to tweak.
So where do I send these questions through? Is that on that page?
Yeah, on the calendar page where you saw the thing, underneath
Yeah.
is like, hey, got questions? Send it through Google Form.
Okay.
And
yeah,
so it'll
sweet.
just be like, send a photo of it or write it up, whatever you want to do to give me all the context that I need.
Oh yeah. Yeah. Sweet.
Easy. All right,
Alright.
I'll leave you to it.
Cool. Thank you.
No worries. Hello, hello. I made it. So many students today. Taking a bit to go through the breakout rooms. How's it going?
It's going okay.
Hmm?
I'm struggling a little bit like when there's a different domain to like the standard, like pi, 2 pi and stuff.
Yeah, okay, so we're talking back to solving circular functions or
Yeah.
sketching.
Yeah.
It is both. Is it both?
Not really sketching. Sketching is okay
Yep.
because we do the period and stuff. But like
Yeah.
when we're solving with a different like domain, like
Hmm.
say for example the questions where like there's t, right? And t is seconds or time.
Oh, yeah, okay. And
I'm
then,
having some trouble with like readjusting the domains and stuff.
oh, okay, so I might be misunderstanding. So we're talking when you mention specifically t and time, are you talking about like how to get from a t value to a time value, like t equals 3 to 3 a.m., that sort of thing?
Oh no, not that.
Yeah, because I thought you meant like going between like plus minus 2 pi when solving circular functions. Maybe
Like
maybe
say,
easier. Is there a question you can point out that's
yeah, say there's like questions 2C and 2D.
2c 2d of the ones we're just looking at recently?
Yeah, of 14N.
Yeah, 14n 2c 2d. Find times. Yeah, okay, so not quite. Oh, right, because it's 0 to 5. Are you doing this tech free?
Mostly, yeah.
Yeah, okay, understood. Oh, damn it, the phone crashed. I did bring it in. I would like to write it down, but it was working for the other ones. Why did it crash now? Okay, so basically, finding times, you probably found the first period worth of solutions, have you?
Yeah.
Okay, cool. Basically put, before you do the divide by 3 on all your solutions, you just plus or minus 2 pi on all of your solutions to get where you're trying to go. All right, because it's still plus minus 2 pi because by default your circular function has period 2 pi, and it should be that when you're doing your rearranging,
Okay.
it should sort itself out.
Yeah, so when I had so I got down to sine 3t is equal to 1.
Yeah.
And I let 3t be y. So then I got like
3TB.
y
Oh, yeah.
is equal to pi over 2, 5 pi over 2, 9 pi over 2, etc., right?
Mhm.
And then when I put 3t back, I get pi over 6, 5 pi over 6, and 3 pi over 2, and so on.
Mhm.
But I don't know when to end it. Like, how do I compare that t domain to, like, it's in
Oh,
terms of pi, and then how do I
yeah.
compare it to like a number?
Yeah, it's going to be real hard for you to compare that. The only thing you can really do there in a tech free is to know that pi is roughly 3.14. And so if you replace it with 3, yeah, you're not going to be able to. Yeah, I just realized the issue. You'll get t values. Yes, you get those in terms of pi, which is perfectly fine. These are intended to be tech active, so you are supposed to convert it to a decimal, and then you'll have a whole number, which is the number of hours, and you'll have a decimal number, which will be your minutes. Yeah, that's why you're having trouble with it. Okay.
Yeah. Other than that, then it's not too hard because also we've done this once before with you.
Yeah, I think this might even be the third time in the
Yeah,
in the
maybe
iterations, because I've done all the classes offset from each other, so they all do it. Oops, that's double audio there.
Okay, yeah. Well, if that was because they usually like that blue tab on the side of it, where it says CAS or not CAS.
Yeah, it's so bad at doing that, isn't it?
Yeah,
doesn't-
on the side it didn't say CAS, so then I was like, I'll just do it tech free. And
Yeah.
I guess I've gotten it to the point where I can in terms of tech free, but then yeah, that's where I got stuck. But now
Yeah.
that like you told me that this is usually tech able, then that's okay.
Yeah, which is even strange because look at this. Then it has CAS underneath it as 5, and it's like, really?
Yeah.
But
I
no,
mean, they may as well just make the whole thing CAS.
because yeah, did you grab a copy of the solution doc?
Yeah, yeah, one of my year 11 peers has sent me the solutions for.
Oh, okay, you got it from elsewhere. Yeah, okay. It's
I
also in
haven't-
the Google Drive as well. So, but
Yeah.
anyway, you've obviously got it. Point is, I think even in the solutions, they'll tell you that they've got, okay, here's the pi values, but here's decimals. And as soon as you see decimals, you're like, okay, yeah, this has got to be
Yeah,
tech active.
that's what I was looking at the decimals and I was like, there's no real way I could do that tech free, so
Yeah, correct. But no, okay, at least you're doing that fine, which is a much easier fix than what I thought we were going to do, which was try to figure out how to do different domains. This is more so using units, basically, is how I'd probably describe this, trying to get it into the right unit. But no,
Yeah.
you're doing fine.
And when like could you show me a question where we would be readjusting a domain?
Now, do you mean again like what we just discussed here, or?
No, like when there's a X translation inside the brackets, like
Yeah, okay. Yeah, I can actually pull up one from the pre-worked solutions. Let me grab that. Solving circular functions. Let's see, how complicated did I make this? Yeah, I made it quite complicated. So yeah, the basic premise is take this and replace it with something. So like how you did y equals 3t, I'm doing u equals all of this inside the bracket.
Yeah.
All we're doing from there is taking whatever the domain was that we had and then putting both of those into this equation that we just created. So
Yeah.
you'd have like a y here instead, but you'd put 0 in this spot, solve it, 2 pi in this spot, solve it. That's what these two sets of workings are about.
Yep.
And so all that means is, instead of having all this there, you put a u there. Instead of having the original domain, you have these values instead.
Yep.
Is that all you wanted to just quickly look over?
So then, yeah, okay. So that's just how it changes, basically. You got to solve.
Yeah, then you just go to solve. It's like, okay, where's cos equal to a half? Well, that's going to be these two spots. And then you're plus or minus 2 pi to your heart's content until you extend out of the domain.
Right. So all we do is just sub in like the upper and lower bounds, and then
Yeah.
Right.
That's what I do anyway, because I like to know ahead of time how far I've got to go. Technically speaking, you can just keep plus minusing 2 pi, unwrapping things, and then seeing, do I have room to go? I don't really like doing that because it feels like I'm doing a lot of rework over and over again.
Yeah. That's fair enough.
So that's why I do that. Just putting the disclaimer, technically speaking, you have two options here. So if this is still weird to you, then feel free to just do the guess and check forever.
Yeah.
That's what
Yeah.
I did. I did this like God knows how many years after school because I was like, okay, how can I teach this better? And then this is
Yeah,
what
okay.
I came up with.
Yeah. Okay. Cool.
But yeah, all right, cool. I'll leave you to play with that for a bit. Seems like you're doing good.
Yeah. Thank you.
No worries.